S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Different solids have different structures, but have you ever, thought about this, that how do we get to know the kind of arrangement atoms and molecules will have in these solids, which decides the geometry of these solids. Welcome to S. Chand Academy, myself Dr. Mamta Sethi. So today I will be discussing with you the techniques to find out the structure of solid, and as an example we will be discussing the structure of few crystalline solids. To study this particular topic in more details, you can refer to the book by S. Chand Publishing. The link to the ebook is given in the description box. So we all know that there are variety of rays which are part of electromagnetic spectrum, but why only X-rays? We utilize X-rays in order to determine the structure of these solids. So the branch of the science or which deals with determining the structure of the solids is known as X-ray crystallography. Right? So the branch of science which helps us in knowing the structure of these solids is known as X-ray crystallography. X-ray, because we use X-rays in order to find out the structures of these crystals, and crystallography because we are finding out the structure of these crystals, right? But how do these X-rays plays an important role, and why particularly only X-rays are selected for this purpose? Now let me answer the first question, that why X-rays are only chosen for this particular purpose. It is simply because of the reason that interatomic spaces, we have these different planes in the crystal. The spacing between these planes exactly matches with the wavelength of the X-rays, and it is because of this reason that X-rays are used to see the reflection from the crystallographic plane, and hence help us to determine the structure of the solids. By structure I mean how the atoms or molecules or ions are arranged in a particular solid. Now there is a fundamental law which is called Bragg's law. It is the law which gives us a very simple relationship between the wavelength of the X-rays, interplanar distance, and the angle at which the reflection will take place. So let me quickly derive the mathematical expression for Bragg's law. Yeah, so these are two crystallographic plane, horizontal crystallographic plane. The distance between these planes is small d, right? So this is your interplanar distance. Now this is our X-ray, let's say ray 1, right? So it is falling at an angle and strikes the surface of the crystal at an angle theta, right? Now the law of reflection says that the angle at which it strikes the surface, with the same angle it will leave the surface also. Therefore the angle of incidence is equal to the angle of reflection, and this will be reflected from the surface in this manner. Now let's say the second ray also strikes the surface, right? These are all X-rays, right? X-ray 1 and X-ray 2, right? Now the X-ray 2 is striking on this particular plane. It is not striking the same plane because it is slightly displaced from the first ray, so it will strike the second plane at this point, and again it will get reflected in the manner which has been shown in the figure. Now this distance, so this point we can imagine point 2, and this distance, as I've already mentioned, is D. Now by applying the simple rules of geometry, we know that what is this angle? This is angle theta, right? Now we can easily see that ray 2 covers additional distance inside the solid. How much additional distance does it cover? You see, this particular point is at par with this point. So how much extra distance? Extra distance A, B, C. So the second ray travels AB plus BC. This much distance it does travel in addition to the distance travelled by ray 1 in the crystallographic planes, right? So the simple rules of optics suggest us that in order to have these two rays in phase with each other, so if we want that ray 1 and 2, as they have been in phase during when they were falling on the crystal, they should be reflected also in the same manner, like they should be in phase. So the simple rule of optics suggests that the distance which they cover, so the path length which they cover in here, in addition to the ray 1, it should be integral multiple of the wavelength. So in other words, I can say that in order to have the constructive interference, in order to have the bright point, bright spot, what should be the condition? The condition is that the path length, which it covers, should be integral multiple of the wavelength of the X-rays, right? Now we can easily see over here that this distance is D, this distance is this angle is theta, and this is your right angle. Now this particular triangle and this triangle, applying the rules of geometry, are congruent triangles. Now the parts of congruent triangles are similar, so we can say that AB, distance AB is equal to BC, congruent parts of congruent triangles, simple theorem. Inserting AB equal to BC in this particular equation, what do we get? We get n lambda is equals to twice AB, right? So what is this distance AB? So we can determine this distance AB from this particular triangle. It will be equal to, if this distance is D, this is theta, what will be my distance AB? AB will be equal to D sine theta. So sine theta, or I can say sine theta equal to AB by D. So I can write this value of AB equal to sine theta and substitute it in, let's say this is equation number 1, I substitute this value in equation number 2 and I get this value. Lambda is equals to, or to be more specific, I can write n lambda is equals to 2d sine theta. So this particular equation is known as Bragg's equation. Now for your information, let me tell you that Bragg was the first one who studied the crystal structure of NaCl using X-rays, and it is for this reason he was awarded with Nobel Prize also. So this particular equation tells us about the the angle at which the reflection will take place from the crystallographic plane. It will not be taking place at any angle, but the angle which is given by this particular equation. Now we see that n lambda equal to 2d sine theta. Now for a given crystal, d is fixed, right? D is fixed, and therefore lambda will depend upon what? Lambda will depend upon angle of reflection. So, and this n also. So the maxima or the bright spot on these X-ray crystallographic studies will be observed whenever the value of this sin theta will be maximum, right. So we will get at a definite intervals, we will get reflections or bright spots, and with the help of these bright spots, wherever we get bright spot, it means there is presence of certain atom, and with the help of these bright spots or constructive interferences, we will get to know the exact structure of any solid. In fact, X-ray crystallography is utilized to find out the structure of any molecule, not only solids, of any molecule. This is the only branch of science which gives us the exact structure of any molecule, right. With the help of X-ray crystallography, it has been found that the solid exist in different forms, and these are the various types of crystals which we have. Now, various crystal types based on their constituent particles. If the lattice positions are occupied by ions, we call them ionic crystals. The example of the ionic crystal is common salt, which we use in our daily day-to-day routine in our kitchens. And what are the kind of forces which binds these ions together? We know that if there are ions, right, there will be sodium ions and there will be chloride ions. So the forces which binds the ions together are electrostatic in nature. Right? Electrostatic forces are very strong forces. It is because of the existence of these strong forces, the ionic crystal are very hard. They have high melting point, right, and they are soluble only in polar liquids, right. We know the rule that like dissolves like. So these are also, the crystal is also polar, so it will be soluble in polar liquids, and it is because of this reason NaCl gets dissolved in water very quickly. Now, if the lattice positions in a crystal are occupied by atoms, we call them atomic crystals or covalent crystals. Now, since there are only atoms, right, so there is no question of ions here, so only atoms. So atoms are connected to each other via what? There are shared electrons, right. So there are covalent forces which binds these atoms together. The very common and very important example of a covalent crystal is diamond, where the carbon atoms, 4 carbon atoms are attached to each other in a tetrahedral fashion. Now, what is the speciality of these covalent crystals are that they are again very hard because of high magnitude of these forces, high melting point, and since these are non-polar, diamond, have you ever given a thought that diamond can be dissolved? No. Because these are highly non-polar, so they will be insoluble in most of the solvents, most of the polar solvents, right. And then if we have instead of atoms, we will have metal ions like sodium ions, and there are electrons present. Such crystals are known as metallic crystals, right. So metallic crystals are there in which metal ions are embedded in the pool of electrons. Sodium crystal is the example of a metallic crystal. The speciality of these crystals are that they are malleable, they are ductile. We know the properties of these metals, that metals can be drawn into very thin sheets, they have luster, they are highly shining, and they are, of course, due to the presence of the electrons, they are very conducting, highly conducting in nature. And lastly, we have molecular crystals. See, if the lattice positions are occupied by molecules and these molecules are held together by van der Waals forces, these crystals are called as molecular crystals. The example of such a crystal is, let's say, methane. They are very soft, they have low melting point, because we know that van der Waals forces are what? Very, very weak forces, right? So the kind of forces which holds these molecules together, if they are weak, definitely the hardness of the solid will get hampered, and it is for this reason that these crystals are soft, low melting point, and they are, because they are what? They are covalent in nature, therefore they will be dissolved easily in covalent solids, right? So now, having understood the concepts, basic concepts which were used in understanding the structure of these solids, let us take a particular example of the solids, right? Let's take the example of NaCl. Understand that how a single crystal of NaCl looks like. What is the arrangement of sodium and chloride ions in a sodium chloride crystal? Now, sodium chloride crystal, as we can see in this particular unit cell, which is of sodium chloride, and these ions, sodium ions and chloride ions here are arranged in FCC, face centered cubic fashion. We have already understood what does FCC means. So here, these small circles, they represent the sodium ions. So we can easily see over here that each sodium ion here is surrounded by how many? It is surrounded by 1, 2, and then 3, 4, and 5 and 6. So each sodium ion here is surrounded by 6 chloride ion, and vice versa, means each chloride ion is also surrounded by 6 sodium ions, and therefore what is the stoichiometry of this particular crystal? The stoichiometry of this crystal is 1:1. 6 sodium ions, 6 chloride ions in a unit cell, and therefore the stoichiometry and in FCC fashion. So this explains the structure of sodium chloride, the lattice. Now, we can have a similar kind of the solid, which is KCl, potassium chloride. The structure of potassium chloride will be identical to that of sodium chloride. The only difference will be here the sodium ions will be replaced by potassium ion, and therefore the size of these ions will be slightly different, right? So one example of FCC arrangement we've already seen. So let me explain you another type of the crystal lattice, which is your cesium chloride. So what pattern cesium chloride is composed of? What is the arrangement of cesium ions and chloride ions in a unit cell? To have a look at the structure of cesium chloride, we can see here. So see here, this is one unit cell of cesium chloride. Very simple, we've already understood that what is BCC arrangement. What is BCC unit cell? So BCC arrangement means the corners are also occupied. Apart from this, we have one atom at the center. So the central position here is occupied by cesium ion. So cesium is slightly bigger in size, so therefore, of course, compared to potassium and compared to sodium, this is bigger in size. So it is represented here by red color, which is present at the center of the cube, and all other 8 corners of the cube are occupied by 8 chloride ions, right? So what is the, each cesium ion is surrounded by 8 chloride ion in BCC fashion. So this type of arrangement is slightly different from the arrangement that we observed in NaCl. Yeah. So now we have understood that how do these crystals, they look perfectly at molecular level. But do these crystals always exist in this particularly perfect fashion in which I have explained it to you? To get the answer of this question, let us watch the next part of this video.
Hello everyone, I am Dr. Richa Arora and welcome to S. Chand Academy. So I am going to make videos on very important topics of physical chemistry. और topics होंगे solutions, phase equilibrium, conductance and electrochemistry. इन videos में हमारा focus रहेगा basics पे और applications पे. तो ये वीडियोस चाहे आप अंडर ग्रेजुएट स्टूडेंट हो, चाहे आप पोस्ट ग्रेजुएट स्टूडेंट हो, चाहे आप इंटरव्यू की प्रिपरेशन कर रहे हो या किसी एंट्रेंस की प्रिपरेशन कर रहे हो, ये सारी वीडियोस आपके बहुत काम आएंगी। सब्सक्राइब कीजिए एस चांद अकेडमी एंड प्रेस द बेल आइकन टू गेट द नोटिफिकेशंस।
So before we had a break, we had discussed about the structure of sodium chloride, structure of potassium chloride, of cesium chloride, and we had seen that how the atoms or ions are arranged in order to give you a perfectly crystalline structure of a solid, right? But do these crystals, they actually have that kind of pattern? The ideal remains ideal only. Not a single crystal in the nature exists as perfectly crystalline solid. So crystals, they always have some defects. Now what do we mean by crystal defects? If the arrangement of the the particles is disturbed from the ideal arrangement that we have seen in earlier slides, it is called a defect in the crystal. So the deviation of the crystal structure from the periodic crystal structure is called a defect. The real crystals, of course, as I mentioned, are not perfect. Of course, we can minimize these imperfections or defects in the crystal, but we can never eliminate these defects completely. Now, what are these defects and how these defects they affect the various properties of the crystals? So to understand the kind of defects that we observe in solids, we can define two different types of effects. So point defects are there. Point defects if means atoms or molecules, if they are displaced from their positions, right? If they are completely missing from their positions, or they can be occupying some other positions other than their latest positions. That means, in other words, I can say that if they are not occupying the position that have been assigned to them as per the perfect crystal, that means they are deviating from the perfect crystalline structure, and hence we say that the solids have defects. Now these defects can be divided into two types: Schottky defects and Frenkel defects. Now Schottky defect and Frenkel defects are of two types: stoichiometric and non-stoichiometric. Stoichiometric, it means if an ion pair is missing or is occupying some other position, means if ions are missing or dislocating in pair, right? So that means the stoichiometry of the crystal is not disturbed. So if one ion, that is one sodium ion is missing, one NaCl ion would also be missing, that is called stoichiometric defects. And the non-stoichiometric, that if they are not missing or occupying other positions in the stoichiometry which is reflected from their molecular formula, we call them non-stoichiometric effects. So let us understand more about what are these Schottky effects. So what happens in these defects? So we have already seen, let us say, I am drawing for the sake of convenience two-dimensional structures. Suppose these are the ions, this is how they are arranged. Okay, let's say this is my sodium ion, chloride ion, sodium ion, chloride ion, again chloride ion, sodium ion, chloride ion and sodium ion. So they had to be at their respective positions. So what happens in Schottky defect, that one of the ion pairs is missing from the crystal. So what happens that these ions, let's say sodium ion and chloride ion. So one sodium ion and one chloride ion. is missing from the crystal, right? So if it is missing, so of course we know that the perfect geometry or the perfect arrangement of these ions in the crystal gets disturbed. So that means this crystal is no longer a perfect crystal. So this is having a defect. So this type of defect is called a Schottky defect. Now what are the consequences of this defect? The consequences of this defect is that, if you remove the ion pair, one of these ions pair, there can be more also which are missing, this decreases the overall density of the crystal. So overall density of the crystal lowers. Other than that, the overall electrical neutrality of the crystal in fact is maintained, because if one sodium ion is missing, one chloride ion is also missing. Therefore, the crystal remains neutral overall, whereas the density decreases. And now you see that in order to occupy this empty space, what will happen? In order to occupy this empty space, this chloride ion which was earlier present here can jump and come over here, and then what will happen, that this position gets empty and this gets occupied by the chloride ion which was present earlier in some other position. And this type of jumping from one place to another place, this will keep on happening in the entire crystal, which will of course leads to the the kind of defect that we are talking about, Schottky defect. And because of the movement of these charges, these type of crystals are highly conducting. So because vacant sites are present over here, in order to fill that vacant site, some other ion will come and then vacancy will be created at that position. In order to fill that vacancy, another ion will come from another position, and hence this process continues, and therefore we can say that these defects of course causes the conduction in these crystals. Now in Frenkel defect, what happens, that the ion pair is not missing from the crystal, right? So what is happening, they are not completely missing, so they are present. Let me draw the structure. So this ion pair will not exactly is missing, but it leaves its own position and will occupy the lattice site. Means NaCl will not be present at its own position, rather it will try. Now means I am drawing it on the board, maybe these positions are appearing smaller in size to you, but these are actually interstitial. This space which exists between these ions is called interstitial space. So if the ion pairs are not occupying their lattice position, instead they are present in these interstitial sites, so this kind of defect is called Frenkel defect. So an ion pair of course is dislocated from its respective position, therefore the crystal is no longer a perfect crystal, but the overall density of the crystal remains same. So density remains same, because even though they are not present in their on their respective lattice position, but they are present inside the crystal only, therefore density remains same. Electrical neutrality also, so crystal as a whole is what? Is neutral, it remains neutral. And like Schottky defect, Frenkel defects are also responsible for conduction of electricity. So though we say that these are defects in the crystal, but actually these defects play an important role which gives some characteristic properties to these crystals. Some good thing is happening in the crystal because of these defects. These crystals become conducting, which earlier they were not. The examples of Frenkel defects are AgBr in silver bromide and ZnS. These kind of defects, they do exist. Next type of defects that we can have are your non-stoichiometric. These are the other class of defects that we have. The earlier two types that we have discussed were examples of stoichiometric defects. Now we are going to discuss about the non-stoichiometric defects. Non-stoichiometric defects means where the stoichiometry of the crystal is disturbed. For example, here if it is NaCl, it is 1:1. So that means the number of sodium ions will always be equal to the number of chloride ions. So 1:1 ratio has to be maintained. If this ratio gets disturbed, somehow we call it non-stoichiometric defects. So what happens that if we take NaCl crystal and we heat this NaCl crystal in the presence of sodium vapors. So sodium vapors, it means we have sodium atoms. So at high temperature, this sodium metal will get ionized. So we will have sodium ion and electron. Now this sodium ion which is present outside, this will get doped into the lattice structure of NaCl. Now since this is Na plus only sodium ion, so it is identical to that of the sodium ions which are present in the crystal. So what will this sodium ion do? They will replace the sodium ions which are present in the crystal, or what it will do, it can also combine with. So this will combine with the chloride ions which are present in the crystal, and therefore from the crystal lattice what will happen? The chloride ion will come out, right? So Na plus and chloride ion will form NaCl, and therefore the chloride ion which has come out, a vacancy has been created over there. So if a vacancy is created over there, in order to fill that vacancy, because it was unit negative charge, electron which is released by these sodium vapors occupies that position. So the position which was earlier occupied by chloride ion is now occupied by electron. So what do we have? We have sodium ions in excess. Chloride ion is less, right? Because chloride ion has combined with the sodium ions which are coming from sodium vapors. So therefore in the crystal, number of sodium ions are less compared to the chloride ion, and hence we can see that the stoichiometry of the crystal is what? It is disturbed. Now this extra electron which has now occupied the position of chloride ion is not sitting at one place. What happens? That it keeps on jumping from one position to another position. So what happens? That the moment this chloride ion, let's say this is your sodium ion and chloride ion, and here we have an electron, and here we have sodium and again chloride ion. The moment this chloride ion will see that there is a vacancy. So what will happen? Chloride ion will come here and occupy this position, and electron will go from this position to this position, and hence this jumping of electron from one position to another position will keep on happening. And now we all know that. Now what is the consequence of this metal excess? Metal excess because sodium is in excess. So metal excess defects is that this crystal appears yellow in color. Now what is the origin of this color? Now we all know that these unpaired electron, this electrons which is moving is getting excited from ground state to the excited state. So it is moving, right? It is going and undergoing transition from ground state to excited state, and from excited state when it comes back to the ground state, it emits energy, and it emits energy in the visible region which corresponds to the yellow color of the visible region, and hence this particular crystal, because of this effect, starts appearing yellow in color. So shining yellow color of this crystal is because of the metal excess defects, and these colored centers, right, are also known as F centers. No? These are known as F centers. The electrons which are jumping, these are delocalized electrons, these are also known as F centers. Now you may be wondering where this F comes from. This F comes from a German word Farbe. Farbe means color. So color center, basically F centers are nothing but they are the colored centers. So another type of the non-stoichiometric defects which we have here is, the earlier one was metal excess defect, now is metal deficiency effect. Now metal will be in deficiency. So these type of effects are generally shown by transition metal compounds. What is the speciality of the transition metals? The transition metals basically have a tendency to exist in variable oxidation state. It can exist in, like for example, iron can exist in +2 also, it can exist in +3 oxidation state also. So what happens in case of metal deficiency effects is that one of the ferrous ions, Fe2 plus ions, is missing from the crystal. It is not present over here. It is missing, right? So if it is missing, what will happen? In order to maintain the total electrical neutrality of the crystal, what will happen? This +2 charge. Had this Fe2 plus ions been here, we would have +2 charge over here. Now this +2 gets distributed to its neighboring iron and converts ferrous into ferric ions. So +1 over here, +3, +1 over here. So this also becomes ferric, this also becomes ferric. So what happens? Overall charge is balanced, but one of the ferrous ions is missing from the crystal, and therefore what is there in excess? Oxide ions are in excess and iron is in deficiency. So therefore such type of defects, we call them metal deficiency defects. So why are they shown by transition? Because iron has a tendency, it can exist in +2 also, +3 also, and it is because of this property that FeO, iron oxide, ferrous oxide, shows this kind of defect. But crystal as a whole remains neutral. The presence of this hole, this is called the vacancy which has been created here, is called a hole, right? This hole lowers the overall density of the crystal, right? Overall density of the crystal is lowered, right? So this is all about the structure of the solids. So in this particular presentation, we have understood that what is the perfect structure of a crystal, how do we determine the structure of these crystals, and we actually come to the conclusion that though we talk about perfection, but the real crystals do have certain defects, and in this particular presentation we have also discussed the kind of defects we can have in these structures. So to read more about this particular topic, you can refer to the book by S. Chan Publishing. The link to the ebook is given in the description box. Please like, subscribe and share, and do not forget to press the bell icon. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.